Have you ever found yourself staring at a really complex circuit diagram and you just feel that wave of dread wash over you? You know, that feeling when you realize a massive wall of differential equations is waiting for you? Well, today, we're going to talk about an incredible mathematical tool that lets you just sidestep that wall completely. Let's jump in and see how it all works.
So let's just get right to it. For anyone who's ever cracked open an electronics textbook, why does analyzing even a kind of simple circuit sometimes feel like such an uphill battle?
Well, it's because when we're working in the normal time domain, we are stuck describing everything with calculus to figure out what a circuit like this one on the left is doing over time. To get these response curves you see on the right, we have to write and solve these big, messy systems of differential equations. It works, for sure, but man, is it clunky.
And that really brings us to the heart of the problem. The traditional way of doing things literally pits you against this wall of differential equations. It's the main obstacle that makes analyzing how a circuit behaves so incredibly tough. Yeah, basically, we're forced to use calculus to describe how things like inductors and capacitors store and release their energy. It's super accurate, but it is not user-friendly. The good news? Oh, there is a much, much better way.
And that shortcut? Well, that's the hero of our story today, the Laplace transform. It is a technique that just fundamentally changes the game for analyzing pretty much any linear system.
So what is this thing really? Simply put, the Laplace transform is a mathematical tool that takes your problem out of the time domain, where all that nasty calculus lives, and moves it into a new space called the S domain. And in the S domain, all that calculus magically turns into simple algebra.
And this is where it gets really cool. Just look at how dramatic this simplification is. Taking a derivative in the time domain, that just becomes multiplying by s in the S domain. And integral, that's just dividing by s. All those complex operations that make up our differential equations, poof, they're suddenly just basic multiplication and division. It's incredible.
Now, to use this superpower, we first have to learn the new language. And that means we've got to take our familiar circuit components, our resistors, inductors, and capacitors, and translate them into their S-domain equivalents.
Let's start with the easy one, a resistor, right? Its whole deal is described by Ohm's law. And luckily for us, when we pop it over to the S-domain, it looks exactly the same. V equals I times R. Nothing changes. Nice and simple.
Okay, now things get really clever. An inductor's voltage depends on the rate of change of current. That's calculus. But when we transform it, it just becomes a simple impedance of SL. And the truly brilliant part is that any initial current it might have is automatically included as a simple little voltage source. The calculus and the initial condition are just baked right into the algebraic model. And it's a very similar story for the capacitor. In the S domain, it becomes an impedance of 1 over SC. And just like the inductor, any initial voltage it's holding is neatly accounted for with its own little voltage source. All that dynamic, time-varying complexity is just packaged into a simple static model.
All right, so we've translated all our parts. Now it is time to see the magic happen. Let's actually put this method to work and solve a circuit.
The process is this beautiful three-step recipe. First, you just redraw your circuit using those S-domain models we just looked at. Second, you use your basic circuit laws, like Ohm's law or Kirchhoff's voltage law, to write purely algebraic equations. And third, once you solve for whatever you're looking for, you use an inverse transform to pop the answer right back into the familiar time domain.
And this right here just illustrates the transformation perfectly. On the left, you've got a standard RC circuit. That switch closes, and boom, you've got a calculus problem on your hands. But look at the right. That's its S-domain equivalent. The capacitor is now just an impedance and a voltage source. It's nothing more than a simple voltage divider problem. And the equation that comes out of it reflects that simplicity. You just use Kirchhoff's voltage law around the loop, and this is what you get. It is a basic algebraic equation. We can solve for the current, I of S, without ever, and I mean ever, writing down a single derivative or integral. This is the power of the S-domain.
Now, solving one circuit is cool, but let's zoom out. This whole method doesn't just give us answers for one specific case. It actually reveals something really profound about the circuit itself. By working in the S-domain, we can unlock its fundamental identity.
And that identity is called the transfer function. You'll see it written as h of s or g of s. It's just the ratio of the circuit's output to its input, all in the S-domain. Honestly, you can think of it like the circuit's DNA. It contains all the information about how that circuit will behave, no matter what signal you feed into it.
So, the key takeaway here is this. Once you find a circuit's transfer function, you can predict its entire response. The properties of this one single function, specifically the values of s that make its denominator go to 0, which engineers call poles, they tell you everything about its natural, transient behavior. It is an unbelievably efficient way to get to the core of how a system works.
And here's the real kicker. This isn't just for electronics, not at all. Any system that can be described by linear differential equations, like this mechanical mass spring damper system, can be analyzed in the exact same way. We can transform it into the S-domain, find its transfer function, and predict its motion using just simple algebra.
And that leaves us with a final, really big thought. This method turns the complicated dynamics of energy storage and transfer into something we can solve with high school algebra. So if we can use this framework to simplify and truly understand electrical circuits and mechanical systems, what other complex systems out there, maybe in fields like biology or economics or even control theory, could be unlocked using the exact same powerful idea?